All right, everyone. Welcome to our online lecture. This is going to be so much fun. Today, we are learning about section 8.9 and improper integrals from the Briggs textbook. All right, so before we get going, let me just give you let me give you an interesting observation to start. So, first of all, consider the following two integrals. We have the integral from 1 to infinity of 1 over x dx, and the integral from 1 to infinity of 1 over x squared dx. All right, so the first integral is right here, and the second integral is right here. So at this point, what I want you to do is I want you to think about how much area is actually under these graphs. So these integrals extend to infinity, but let's actually think about how much area is underneath them. So I want you to make a guess for each one, and then in a second, you'll see if you're right. So in years past, I've had people guess everything from, 1 natural log of 2, square root of 2, pi, infinity, etc. For this first integral, the actual amount of area underneath the curve is infinity. There, in fact, is an infinite amount of area underneath this curve when it stretches from 1 to infinity. And this is sort of predictable, right? Like, look at this curve, and you can kind of just think about the fact that there's an infinite amount of area underneath it. For the second one, people will also similarly guess, lots of fun numbers. We'll use the same numbers above. The answer for this second integral is that the area is actually equal to 1. And this should be a little bit surprising because we have an integral that starts at the x value of 1 right here, and it extends towards positive infinity. And it continues on forever. So no matter what x value you choose, there's always going to be a height to this graph, and there will always be some sort of area underneath it. But the idea is that this gets small enough quickly that the area actually ends up being 1 after everything is said and done. And so, yeah, that's a pretty surprising result that we can actually look at some curves and find out that it has a finite area underneath it. Another surprising thing is the fact that the first curve had an infinite amount of area and the second curve had a finite amount of area. So in this section, we are going to discover which curves have finite area, in which case we call such a curve a convergent integral. And if a curve has an infinite amount of area, we call it divergent. And we're going to figure out when certain integrands cause the integral to be convergent and which ones cause it to be divergent. All right, so let's explore that, shall we? So first definition, an integral is considered improper. Let me see if I can switch colors. There we go. It is considered improper if the top bound is infinity or the bottom bound is negative infinity. So if you have an integral that's like 1 to infinity of some function, or if you have negative infinity to some number, let's say like 0. These are both type 1 integrals. In the second case, an integral may be considered improper if the integrand becomes unbounded on its interval. That's a type 2 integral. And we will talk about those more in a minute. If an improper integral has a finite area underneath it, the integral is said to converge. Kind of spoiled that for you. We discovered that on the last slide. Converge, so I have to erase this. And then if it has an infinite amount of area, the integral diverges. All right, so let's explore how we evaluate a type 1 improper integral. The fact that it has an infinity in the bound is a little bit challenging for us, but one way we can kind of think about this is if we rewrite this as a limit. So what we will do is we will rewrite this as the limit as b approaches infinity of the integral from 1 to b of 1 over x squared dx. And so this is an equivalent calculation, and the idea is that now we can work with a finite b and just plug that in, and then at the very end of the problem, we will finally take the limit as b approaches infinity and see what happens. All right, so if we evaluate this, remember that 1 over x squared is really just x to the negative 2, and so whenever we integrate that, we increase the power by 1. So we're going to keep this limit throughout the problem. This is going to be, so we increase the power by 1, so now it's negative 1, and so it's negative 1 over x. And we divide by that new power, which is negative 1, which is where we come up with that. And we are evaluating from 1 to b. So now we are going to plug in our bounds of b and 1. So we're going to get negative 1 over b minus negative 1 over 1. And this is just equal to the limit as b approaches infinity of negative 1 over b plus 1. All right. And one thing to know is that whenever you are doing a limit problem, one fact that we have is that, why did the pen become so thick? That's weird. Okay, hold on. That's better. But now I gotta erase stuff. Okay. Whenever you're doing a limit problem, the limit of anything of f of x plus g of x, I really have no idea why it's doing that, is equal to the limit as b approaches infinity of the first one plus the limit as b approaches infinity of the second function. And so that's basically what we're doing. We're just splitting it up. And so we have the limit as b approaches infinity of negative 1 over b. And the idea here is that whenever you actually think about what this is equal to, this limit should just be 0 plus 1. And so that gives you just an answer of 1, which is exactly the answer that we got on the previous slide, which gives us some evidence to believe that we are doing this correctly. All right. One thing about notation here is that, let me switch colors. We want to make sure that we do not write 1 over infinity. This is bad. We don't want to actually plug in infinity at any point during our calculations. It's notationally incorrect because infinity is not a number. So try to avoid that if you can. All right, next we are going to summarize what happens with type 1 integrals. So the idea is that suppose we have a f as a continuous function on a to infinity, then the integral from a to infinity of f of x dx is equal to, as we just did in the last problem, the limit as b approaches infinity of the integral from a to b f of x dx. And similarly, if we have a continuous function from negative infinity to b, then the integral of negative infinity to b of f of x dx should be written as the limit as a approaches negative infinity of the integral from a to b of f of x dx. We're just getting rid of that infinity in the bound, replacing it with a limit. And then we will calculate the integral as normal, and then just calculate the limit at the end. There is something special we have to do if we have infinity in both bounds, if negative infinity is in the bottom bound and positive infinity is in the top bound. In such a circumstance, we are going to have to split up the integral into two pieces. And so you can actually notice what that looks like here. We are going to write that the integral from negative infinity to positive infinity of f of x dx is equal to the limit as a approaches negative infinity of a to c, where c is just any random number. So c, in this case, could be equal to 5, if you wanted it to. Or c could be square root of 2. Really just anything. And then we add that to the limit as b approaches infinity from c to b of f of x dx. And then this will give us the full value for the integral. As it says below, the choice of c does not affect the value or the convergence of the original integral. All right, if any of these integrals give you a finite number, so that's not infinity, not negative infinity, then the improper integral is said to converge. Otherwise, they diverge. Let's do an example. Suppose we have the integral from 0 to positive infinity of e to the negative x. All right, so we are just going to rewrite this as we did with part 1 of that definition, where we have a as a bottom bound and infinity as a top bound. We are going to write this as the limit as b approaches infinity of the integral from 0 to b of e to the negative x dx. And this is pretty easy to evaluate. This is just negative e to the negative x, evaluated from 0 to b. And then if we finally plug in b, we're going to get negative e to the negative b minus negative e to the 0, which is just the limit as b approaches infinity of negative e to the negative b. All right, so e to the 0 is 1, so we are really just adding a 1 here. All right, and so now here's where we have to be a little bit careful. We have to think about what the limit as b approaches infinity of negative e to the negative b is. Let me do this with a different color. Let's do blue. So negative e to the negative b is really equal to negative 1 over e to the b. And so if we think about what happens whenever we plug in infinity, this whole thing will approach 0 as b approaches infinity. Okay? And so, if that whole thing approaches 0, let's write it like this. That whole thing approaches 0. And so, we get, as an answer, 1. And so this integral, therefore, is convergent, because we got a finite value. And so this curve, e to the negative x, also has an infinite, or has a finite amount of area underneath it from 0 to infinity. So that's another neat little result. So once again, a common notational error on these sorts of problems is that people will plug in infinity. So people will write negative e to the negative infinity plus 1. and this is not good. This is bad notation. Don't plug in infinity. All right, let's try another example. Also, I recommend that you try these on your own first, before I work them out. See if you get the same answer. All right, so hopefully you've tried to work this one out. If not, then just enjoy the show. In this case, we have negative infinity in the bottom bound and positive infinity in the top bound. And so the first thing that we need to do for this sort of problem is we need to split it up. We need to split it into two pieces. So let's start by rewriting it like this. Let's not write the limit quite yet. Let's write this as the integral from negative infinity. And so we can choose any real number that we want to illustrate that this is truly an arbitrary decision. Let me choose 1738. And then we are going to split up the integral right at that number. So this is the same as the integral from negative infinity to 1738 plus the integral from 1738 to positive infinity. Okay, next we rewrite with a limit. So this is the limit now as b, let me say a. Limit as a approaches negative infinity of a to 1738 of dx over 1 plus x squared plus the limit as b approaches infinity of 1738 to b dx over 1 plus x squared. Whoops. Okay. Come on. All right. So let's continue with this calculation. We can compute this integral. Hopefully you guys remember that this is indeed the integral of just the arctangent. And so, in order to evaluate this integral, we write that this is just the inverse tangent of x evaluated from a to 1738. And then it's going to be the same calculation over here of the arctangent of x evaluated from 1738 to b. Alright, and so then we are going to plug everything in. I'm going to give myself a little bit more space. We still have a limit, and notice that we have two different limits here. We have the limit as a approaches negative infinity and the limit as b approaches infinity. It is good notationally to use two different letters. You don't want to use b for both this limit and this limit. So I recommend using two different letters for these two different limits. Alright, so anyway, we're going to plug this in. This is going to be the arctangent of 1738 minus the arctangent of a. And then over here we have the limit as b approaches infinity of the arctangent of b minus the arctangent of 1738. Alright, so the next thing to notice in this problem is that we have some cancellation. Specifically, since this term here doesn't have an a in it, it is just equal to itself. It is a constant. The arctangent of 1738 is just some number, right? And so this number and this number, also a constant, will cancel out because we have a positive arctangent of 1738 and a negative arctangent of 1738. So those will just cancel out because the limits don't affect them. All right, and so that's going to leave us with the limit as a approaches negative infinity of negative arctangent of a plus the limit as b approaches infinity of the arctangent of b. Alright, so here is a hard step. We have to think about what these limits are equal to. So the way that we come across an answer for this is to recall what the graph of arctangent looks like. Okay, this is annoying. How do I get this to work? Technology is really fickle. Okay, let's try again. Nope. There we go. Okay, we need to figure out what the graphs for arctangent, or what the graph of arctangent looks like. So, maybe one thing that you have tucked away in your brain is that for the graph of arctangent of x, the idea... Oh my god, I don't know how to deal with this. Okay, we're going to edit this out. Okay, we're going to figure out what the graphs for arctangent look like. So the idea is that the arctangent graph looks a little something like this, where specifically it has horizontal asymptotes right here and right here, and the values at which those occur are negative pi over 2 and positive pi over 2. And so the idea is that the limit as b approaches infinity of arctangent of b, that thing is just equal to pi over 2. And we can definitely use that information in order to evaluate our integral correctly. All right, so specifically down here at the bottom, we have the limit as a approaches negative infinity. Let me no longer throw in that a. or that limit. Let me just go ahead and calculate it. So if we evaluate this limit, this is going to be negative pi over 2. The first negative comes from the fact that we have a negative right here. The second negative comes from the fact that the limit of that thing is negative pi over 2. And then for the rightmost piece, this is going to be positive pi over 2 for a grand total of pi units. And so this integral as well is convergent. All right, so that's an example where you have negative infinity and positive infinity in both bounds. All right, let's now explore a very special integral. This is 1 over x to the p, where p is just some integer, or actually just some number. Doesn't have to be necessarily an integer. Okay? There's 3 cases that we're going to break this up into. The first case that we will consider is whenever p is greater than 1. The second case we'll consider is whenever p is less than 1, and then finally we'll consider when p is equal to 1. And you'll realize that this integration heavily depends on which of those cases we fall into. So this integration is a very common one. In fact, both of the integrals that we did on the first slide fell into this category of integrals, where in this case p was equal to 1, and in this case p was equal to 2. Okay, so for case 1, here's the idea. We have that the limit as b approaches infinity of the integral from 1 over b, 1 to b of x over p dx is equal to, let's evaluate this limit. Let's evaluate this integral. All right, so x to the p in the denominator is really just x to the negative p. And so if we increase that power by 1, we're going to get x to the negative p plus 1, or I could write that as x to the 1 minus p divided by 1 minus p. And then this is evaluated from 1 to b. Great. Okay, so the next thing we do is we plug these in. We will get b to the 1 minus p all over 1 minus p minus, so we're plugging in 1 for x. And so 1 to the 1 minus p power is still just 1. And so we have 1 over 1 minus p here. These already have a common denominator, and so we could put it all together if we wanted to. And let's see, what's the best way to write this? There's a variety of ways to think about it. Let's go with the following. We could write this as 1 over 1 minus p on the outside, limit as b approaches infinity of b to the 1 minus p minus 1. Okay, so here is the key observation. If p is greater than 1, that means that 1 minus p, if we subtract p from both sides, this has to be less than 0. So if 1 minus p is less than 0, that means that this power over here is less than 0. And since that power is less than 0, b, the limit as b approaches infinity of b to a power less than 0, that will be 0. Okay, so just for example, let me write something off to the side. Limit as b approaches infinity of b to any negative number, let's say negative 5. That is just the limit as b approaches infinity of 1 over b to the 5th. That is just 0. And so that whole limit there is 0 minus 1. Alright, and so this is equal to just negative 1 over 1 minus p, or we could rewrite this as 1 over p minus 1. And this is a finite number for any p that you give me. And so this is convergent. All right, and so the conclusion is that, let me write it in a different color, is that if p is greater than 1, then the integral from 1 to infinity of 1 over x to the p dx is, okay, my pen is somehow bleeding, which makes no sense because this is an Apple Pencil. Let's try again. Dx is convergent. And not only is it convergent, it equals 1 over p minus 1. So I can guarantee you the answer already. And in fact, this matches up with the very first slide we did, because we said that if p was 2, then we would get 1 as our integral value. And in fact, we get 1 over 2 minus 1, which is indeed just 1 as our overall area, which makes sense. Okay. Next, let's explore the case whenever p is less than 1. So, in this circumstance, much of the steps will be the same. We have that the integral from 1 to infinity of 1 over x to the p dx is equal to a bunch of steps. The limit as b approaches infinity of b to the 1 minus p all over 1 minus p minus 1 over 1 minus p. Once again, we could bring out that 1 minus p power, or 1 minus p in the denominator, I mean. And we just get b to the 1 minus p minus 1. All right. So in this case, if p is less than 1, this means that 1 minus p is greater than 1 if we were to subtract p from both sides of this thing. All right, so if 1 minus p is greater than 1, or sorry, not greater than 1, greater than 0, this is greater than 0, then that means that this overall limit is going to be equal to infinity, because that's just a positive number. So, for example, the limit as b approaches infinity of b to the 1/2, that is infinity, of b to the square root of 2, that is infinity, and so this limit just explodes, which indicates that this entire thing is just equal to infinity. And so therefore, since it is infinity, it diverges. The conclusion here is that if p is less than 1, then the integral from 1 to infinity of 1 over x to the p is equal to infinity, and therefore diverges. Okay. Let's explore the case whenever p is equal to 1. Alright, so in this case, we are evaluating the integral from 1 to infinity of 1 over x, because p is equal to 1. And this integration we have to do differently than the previous two, because we know that the integral of 1 over x is just equal to, first of all, let me rewrite with a limit. Let me do that step first. You should always do that step first. So, the integral of 1 over x is just, of course, the natural log of the absolute value of x, evaluated from 1 to b. And if we plug in our bounds, we get the natural log of the absolute value of b minus the natural log of the absolute value of 1. The natural log of 1 is just equal to 0. We're asking ourselves, e raised to what power gives you 1? And the answer to that question is 0. And then the limit as b approaches infinity of natural log of b is infinity, because the natural log graph explodes off to infinity. It does not approach any bound, but it indeed does explode. And so that goes to infinity. And so we end up with the conclusion that this thing is equal to infinity and also diverges. So in this case, if p is equal to 1, then the integral of 1 to infinity of 1 over x to p is equal to the integral from 1 to infinity of 1 over x. And that is equal to infinity, so it diverges. One thing to note here is that this bottom bound of 1 in the integral will not affect the convergence or divergence of the integral. So if I were to change that bottom bound to a 2 or a 3 or a -5, any of those, it would still converge or diverge according to whether p is less than 1, p is equal to 1, or p is greater than 1, like in the first case. However, in the first case, if we do change the bottom bound, then this will no longer be true. It will no longer necessarily be equal to 1 over p minus 1. The actual answer to that integral will change, but it will still converge. Okay, so summarizing. If we have the integral from 1 to infinity of 1 over x to the p dx, we get the following result. This is equal to 1 over p minus 1 if p is greater than 1, and it is equal to infinity, i.e. it diverges, if p is less than or equal to 1. The way that I like to think about these sorts of functions is that if you compare 1 over x to 1 over x squared, the 1 over x squared graph approaches 0 much quicker. Approaches 0 quicker. And that is my intuition in how to remember whether it is 1 over x that converges or 1 over x squared. It's my intuition to remember that we need p greater than 1 in order to converge. So if it approaches 0 quicker, then it's going to be a smaller overall area. Okay, and as I wrote at the bottom, this is sometimes called the p-test for integrals. Later on in Chapter 10, we will learn about the p-test for series, but right now we are just dealing with infinite integration. Okay, now let's explore type 2 improper integrals. Consider the integral 0 to 1 of 1 over root x dx. So at first, this integral may not seem improper since neither bound includes infinity or negative infinity. However, notice that the integrand, remember that the integrand is just the thing inside the integral, the integrand is unbounded at x equals 0. So here's a picture of the graph down below. As the graph gets closer and closer to 0, this thing will explode off to infinity, and so the overall integrand is unbounded at that point. All right, and so in other words, at x equals 0, let's see, what did I want to write in this blank? At x equals 0, the function explodes. All right, so here's the question. Does this integral converge? We have to ask ourselves what happens whenever this integral gets closer and closer to 0. So here's the calculation. The integral from 0 to 1 of 1 over root x dx should be written as a limit again. But this time, we don't have a limit as something approaches infinity. We have the limit as this c value approaches 0 from the right. So we're going to write it like this. The limit as c approaches 0 from the right. And it is the left bound of our integral. So the bottom bound of the integral, which is approaching that. Top bound is fixed at 1. And the integrand, we can just write as x to the negative 1/2. And we just evaluate this like normal. So we have the limit as c approaches 0 from the right. Remember that plus sign in the exponent means that we are approaching the number 0 from the right of 0. So this area is to the right of 0. Okay. So the integral of x to the negative 1/2 is just x to the 1/2 divided by 1/2, evaluated from c to 1. All right, and so now if we plug in our bounds, if we plug in 1, we will just get 1 divided by 1/2, which is just 2. If we plug in c, we will get the square root of, let me see, let me not quite write it like that. Let's go with 2 square root c. All right, and in order to evaluate one-sided limits, the first thing that you should always try is just plugging in the value. So if we plug in 0 here, we get no issue because 2 minus 0, or sorry, the square root of 0 is just 0, and so we have no problem evaluating that. And so this is just 2 minus 0, which is 2, which indicates that the value for this integral is 2, and therefore it converges. So once again with this graph, there is a finite amount of area underneath it, even though the y value of this function exploded off to infinity within our bounds. All right, so let's generalize this. Here's how we do this in general. Suppose that f is continuous on a to b, but the limit as x approaches a from the right of f of x is equal to plus or minus infinity, so it explodes at a. So yeah, what this essentially means is that our function is unbounded at a. Function is unbounded at x equals a. All right, if that is the case, then this limit, or this integral from a to b of f of x dx, should be written as the limit as c approaches a from the right of the integral from c to b of f of x dx. Similarly, if it is unbounded at our rightmost endpoint, at b, that's this case, function unbounded at x equals b. If that is the case, then we are going to rewrite the integral from a to b of f of x dx as the limit as c approaches b from the left of a to c f of x dx. All right, so now our c is in the top bound instead of the bottom bound, like in the previous example. All right, and so the next natural question to ask yourself is what happens whenever whenever the function is unbounded somewhere in the middle of our integral? And similar to what we did with the last problem, we need to split this up into two pieces. So in this case, we split into two pieces. All right, so we're going to suppose that f is continuous on a to b, except at some interior point P, where f is unbounded, so that's this guy. Then the integral from a to b of f of x dx is equal to the limit as c approaches P from the left of a to c f of x dx, plus the limit as d approaches P from the right of d to b f of x dx. So we have split it into two pieces. The first piece is this guy over here, a to c. The second piece is this guy over here. And we ask ourselves, what happens as c and d both approach P? And if any of these limits in cases 1 through 3 exist, then the improper integrals converge. Otherwise, they diverge. Let's do an example. Suppose we have the integral from 0 to 3 of 1 over root 9 minus x squared. Feel free to give this a shot before I do, see if you get the right answer. Okay, so here is the idea. First of all, we must recognize where this integral becomes unbounded. All right, so this integral becomes unbounded at x equals 3. So becomes unbounded at x equals 3. And so this indicates that our limit should be for our top bound of 3. So we're going to write it like this. This is going to be the limit as c approaches 3. And should this be from the right or from the left? In this case, since 3 is the rightmost bound and all of the area is to the left of it, we are approaching 3 from the left. So this is the integral from 0 to c, 1 over root 9 minus x squared dx. All right, there's a couple different ways to evaluate this integral. The easiest one is to recognize that this is the arcsine formula from your 8.1 table and just use that knowledge. You could also do trig sub, although if you did do trig sub, you would have to change the bounds, and that would be so much fun. So I recommend against that. And so we just use our 8.1 table. And that will give us that this integral is equal to the arc sine of x over 3. And then this is evaluated from 0 to c. We're going to plug in our bounds. We get the arcsine of c over 3 minus the arcsine of 0. The arcsine of 0 is 0. I really shouldn't use that arrow notation. I should use something like this. This is equal to 0. The arrow notation generally we use whenever we're evaluating a limit and we say that that thing approaches 0 or infinity or whatever as we approach the limit number. But it's not that big of a deal. Okay. So then, once again, with these sorts of problems, the thing that we want to do next is we ask ourselves, what happens if we just straight up plug in c equals 3 right here? Does that cause a problem? In this case, it does not. So we can write that this is equal to the arcsine of 3 over 3 minus 0. The arcsine of 3 over 3 is the arcsine of 1. We're asking ourselves, sine of what angle gives me 1? And that answer, of course, is just pi over 2. And so our final answer is pi over 2. And so this thing is convergent. All right. Let's keep going. Now suppose that we have the integral from 1 to 10 of dx over x minus 2 raised to the 4/3 power. All right, so this example is kind of tricky because we need to make sure that we take into account that this thing is indeed unbounded at x equals 2. So this is unbounded at x equals 2. It is really easy, really easy to just miss that from the beginning and just try evaluating this integral and go from there. But unfortunately, it won't work. You'll get the wrong answer. So let's notice that since x equals 2 is within the interval 1 to 10, we have to split this integral into two pieces. So we're going to write this, as the integral from 1 to 2 of dx over x minus 2 to the 4/3 power plus the integral from 2 to 10 of dx over x minus 2 to the 4/3 power. All right, and we need to actually integrate these, but first we have to write it as a limit. let me use the common notation that we've been using. So let me say c. So this is the limit as c approaches 2. Since the interval 1 to 2 is left of the number 2, this should be c approaches 2 from the left. The integral 1 to c of dx divided by x minus 2 to the 4/3 power plus the limit, let me use d over here, the limit as d approaches 2 from the right of the integral d to 10 of dx divided by x minus 2 to the 4/3 power. From here, we need to integrate each piece. We're going to carry this limit along. The integral of 1 over x minus 2 to the 4/3 is just going to be as if x minus 2 was just x. So we write this now as, let me do it up here, x minus 2 to the 4/3, and the denominator can be rewritten as x minus 2 to the negative 4/3. We increase that power by 1, divided by the new power. And so we're going to get x minus 2 to the negative 1/3 divided by negative 1/3, evaluated from 1 to c, plus the limit as d approaches 2 from the right of same limit, or same integrand, evaluated from d to 10. Alright, so now we got to plug this in. We are going to have, let me pull this negative 1/3 outside of the limit. So one rule that we have for limits, if you guys remember back to Calc 1, is that the limit as a approaches anything, let me just say number sign, of, let me change this up a little bit. Whoa, what is that? Alright, so alright, so one rule we have for limits is that if you take the limit as x approaches any number of, let's say, go away. I hate this. This is so annoying. Of, let's say, a times f of x, where a is just any number. This can be rewritten as a times the limit as x approaches that same number of f of x. Right? We can just pull the number to the outside of the limit. Alright, great. So, using that information, we can pull that negative 1/3 outside of the denominator and the limit altogether and write it as negative 3 over here. Limit as c approaches 2 from the left of x minus 2 to the negative 1/3, evaluated from 1 to c, plus, once again, negative 3, limit as d approaches 2 from the right, x minus 2 to the negative 1/3, evaluated from d to 10. All right, and we are going to plug in our bounds. We get -3, limit c approaches 2 from the left, of c minus 2 to the -1/3 minus -1 to the -1/3 minus 3, limit as d approaches 2 from the right, of 8 to the -1/3 minus d minus 2 to the -1/3. Okay, hopefully I wrote everything correctly. We can simplify this a little bit. We have -3 limit as c approaches 2 from the left of c minus 2 to the -1/3 power. And then -1/3, sorry, -1 raised to the -1/3 power. Let's think about that for a second. This is really or 1 over -1 to the 1/3 power. So what is the cubed root of -1? That is -1, so this is 1 over -1, which is -1. So that whole thing there is just -1. Since we have a minus -1, this is a plus 1. And then we have -3 times the limit as d approaches 2 from the right of, let me not write that limit quite yet. So 8 to the -1/3 power is equal to 1 over the cubed root of 8, which is 1/2. And so this is 1/2 minus, now I'll write the limit as d approaches 2 from the right, of d minus 2 to the -1/3 power. All right, we have finally gotten to a point where the limits aren't so trivial. So let me rewrite this line on the next slide, and we will continue from there. So we have the limit, actually we had -3 out front, so let's write that first. We have -3 times the limit as c approaches 2 from the left of, we write it like this, 1 over c minus 2 to the 1/3 minus, or we said plus 1, and then -3 times the, let's see, we had 8 there, so this was, this was 1/2 minus the limit as d approaches 2 from the right of 1 over d minus 2 to the 1/3 power. Okay, so the question we have to ask ourselves is, how do we evaluate these limits? The trick for evaluating limits that look like this, where you have a one-sided limit and you can't just plug in that number. So let's think about what happens if we attempted to just plug in 2. we would get 1 over 0, which is undefined. And so therefore, we have trouble whenever we just plug into either one of these limits. So whenever it's a one-sided limit, think about what happens whenever you plug in. Think about what happens when you plug in a number barely smaller than 2. That is for this limit. For this right limit over here, we'll have to think about what happens when we plug in a number barely larger than 2. But for this first one, if we plug in a number that's barely smaller than 2, think something like on the order of 1.999, then we are going to get 1 over a small negative number cubed. Small negative number, not cubed, cubed rooted. The cube root of a small negative number is also a small negative number. And so, this thing we should think about, if we have 1 divided by a small negative number, think like 1 divided by negative 0.000001, for instance, that number we can write as negative infinity, as that thing becomes smaller and smaller and smaller. So, the idea is that this entire limit here approaches negative infinity. Okay? On the right-hand side, let's consider what happens for this guy. So over here, we're going to think about what happens when we plug in a number barely larger than 2. So think, for example, 2.0001. Then we are going to get 1 over a small positive number. Small positive number raised to the 1/3 power. And that, of course, is just 1 over another small positive number. And that will approach positive infinity as that thing, as the denominator gets smaller and smaller and smaller. And so this entire, this entire limit approaches infinity. But since there's a minus sign here, it's really minus infinity. So we can write this. Now, finally, let's return to our nice blue. We can write that this thing is equal to -3, and I don't quite want to write -3 times infinity, and so let's just kind of think about what happens here. So I'm going to label scratch work, so that way a grader knows that whenever I write infinity here, they shouldn't grade it. So what we really have is -3 times negative infinity plus 1 minus 3 times 1/2 minus infinity. -3 times negative infinity, that is actually just positive infinity. negative 3 times positive 1 is negative 3. Negative 3 times 1 half is negative 3 halves. Negative 3 times negative infinity is positive infinity. And so this whole thing is just positive infinity. And so, our final answer, we can finally conclude, after all is said and done, that this whole thing is equal to infinity. And so, therefore, the integral diverges. Alright, one thing to consider, what happens if we have the case when infinity minus infinity occurs? If, for example, one of these infinities was not positive, if one of them was negative. In that case, that would be an indeterminate form, and we studied those back in Calculus 1 whenever we reviewed L'Hopital's rule. And so you would have to go through the efforts of making it into some sort of fraction somehow and using L'Hopital's rule. But for the purposes of this section, we generally aren't that mean. And so if you do see infinity minus infinity, most likely you've made a mistake with one of your signs somewhere. So check to see that one of your signs, or check to see that both of your signs are correct. Okay, let's continue. Alright, so next up we have the comparison test for improper integrals. So sometimes we are faced with integrals that are difficult or sometimes even impossible to evaluate with the tools that we currently have. So think, for example, the integral of a to infinity of e to the negative x squared dx. This is actually a super important integral, and it's used in statistics and probability calculations frequently. The answer is actually really nice. It involves pi. But anyway, this is a really challenging integral to evaluate analytically. And so one way that we can determine whether or not this thing converges or diverges is to use this thing called a comparison test. So here's the theorem. Suppose the functions f and g are continuous on the interval a to infinity, with f being the larger function. This is important. F is the larger function. So let's suppose this is our graph. Here's f, and then over here is g. If f of x converges, then the integral of g of x converges. Okay, so actually let me provide you a better picture, one that's more realistic. The function f might look something like this, and the function g will be smaller than it, so perhaps it does something like this. F is always larger, and suppose that this value right here is a. Okay. Alright, so the idea here is that if the integral underneath the f function converges, if there is a finite area from a to infinity underneath the f function, then that implies that the integral under the g function is also finite. And hopefully that makes intuitive sense, since the area under f is larger than g. So if the integral from a to infinity of f of x converges, then the integral from a to infinity of g of x converges as well. Conversely, if the integral from a to infinity of g of x diverges, then the integral from a to infinity of f of x diverges as well. So if the smaller function diverges, then the larger function will diverge as well. And hopefully that makes intuitive sense also, because the smaller function has an infinite amount of area underneath of it. The larger function must also have an infinite amount of area underneath it. So, yeah, to formally write this down, here's an idea. If the larger function converges, then the smaller function converges. And if the smaller function diverges, then the larger function diverges also. Okay, so that's the intuition here. Let's do an example with this one that I mentioned earlier. It's the integral of e to the negative x squared dx. We are just going to determine whether the integral converges or diverges. We're not going to actually try to compute what it is equal to if it does indeed converge. Okay, so the hint that I have to give you for this problem is that on 1 to infinity, we have the following fact. E to the negative x squared is less than or equal to e to the negative x. And perhaps you can see this on the graph over here at the bottom. The green function is e to the negative x squared, and from 1 to infinity, it is always smaller than e to the x. So we're going to use this information to make the following conclusion. We know that the integral from 1 to infinity, actually we did 0 to infinity earlier, so let me write that down, from 0 to infinity of e to the negative x dx converges. That's an earlier example. All right, so if that's true, then certainly the integral from 1 to infinity of e to the negative x dx converges. Right? The only thing we changed was this bottom bound, so we're taking now less area. So certainly that will converge as well. All right, so then we have that since the integral from 1 to infinity of e to the negative x dx converges, since the larger function, in this case e to the negative x, converges, on the interval 1 to infinity, the smaller function in this case e to the negative x squared converges also. And this is by the comparison test. All right, so the larger function converges, so the smaller function converges also. Okay. So let's do another example. We're going to determine whether the integral 1 to infinity of 1 over the cubed root of x squared minus 0.5 converges or diverges. All right, so the trick for problems like these is that we need to find a function to compare our integrand to. So we need to find a function to compare 1 over the cubed root of x squared minus 0.5 2. And specifically, we need to compare this to a function for which we already know the convergence behavior. So, let's write that down. We want to compare to an integral to a function. For which we know the convergence behavior. All right. So, there's not many integrals that we know the convergence behavior for yet. But one thing that we do know is integrals of the form 1 over x to the p. We just discovered what happens with those. So how about we compare this to the closest thing that resembles our integrand? How about 1 over x to the 2/3? All right, so the thing that we need to do whenever we are doing the comparison test is we actually need to compare the functions. So how does the function 1 over cubed root, x squared minus 0.5 relate to 1 over the cubed root of x squared? Which one of these two functions is larger? Think about it for a second. So the idea here is that this function on the left is subtracting a number from the denominator. Since the denominator is smaller, the overall function is larger. Okay, so now that we've established the relationship between these two, we next need to check, does our integral, so here's the question, does the integral 1 over x to the 2/3 converge or diverge? And the answer, think about it for a second, the answer is that it will diverge by the p-test. Because p is equal to 2/3, which is less than 1. And this notation here is very important. Make sure you write this, especially on your exams. We will take off if you don't. I had one student a few semesters ago who neglected to write this particular fact, and that was the only thing he missed on the entire exam. He got a 99.5 and he was really upset about it. So make sure that you get this notational fact correct. Alright, so with this in mind, since the integral 1 over x to the 2/3 diverges, and that is the smaller one, that means that the larger integral must diverge as well. So let's write it out for completion. Also, if you're not familiar, this symbol here means therefore. The 3 dots in a triangle, it's the mathematician's way of saying therefore. Therefore, since 1 over x to the 2/3 is less than or equal to 1 over cubed root x squared minus 0.5 on the interval 1 to infinity, and the integral from 1 to infinity of 1 over x to the 2/3 dx diverges the integral from 1 to infinity of 1 over the cubed root of x squared minus 0.5 dx diverges also. By the comparison test. All right, so the smaller function diverged, therefore the larger function has to diverge as well. Okay, next up, we're going to determine whether the integral 1 to infinity of 2 plus cosine of x divided by x squared converges or diverges. The hardest part of this sort of problem is identifying the appropriate function to compare this thing to. All right. So, let's write that down. What to compare? 2 plus cosine x all over x squared 2. Let me present to you with a fact. This fact will be used throughout the next several sections, so it is a good one to know. For sine and cosine, they are both bounded between -1 and +1. And that is true for any x. Okay? So if we use this fact, then 2 plus cosine of x, this implies that 2 plus cosine of x all over x squared is less than or equal to 3 over x squared. In fact, we could even write a little bit further, which I think I will. Let's write that this is greater than or equal to 1 over x squared. Okay? And with this knowledge, the important one to know is this guy. And you'll see why in a second. The idea here is that since we only care about the interval 1 to infinity, we'll write that this is true on 1 to infinity. We know that the integral from 1 to infinity of 3 over x squared dx converges and this is because p is equal to 2, which is greater than 1. And so that uses the p-test. And so what we have essentially found is we found a larger function that converges. So a larger function converges means that a smaller function must converge as well. So let's write that in words. Since 2 plus cosine x over x squared is less than or equal to 3 over x squared on the interval of concern, 1 to infinity, and the integral from 1 to infinity of 3 over x squared converges the integral from 1 to infinity of 2 plus cosine x all over x dx converges also by comparison test. So I would argue that this is a pretty tricky concept. It's one that is not entirely obvious. First of all, we have to utilize this fact that I gave you, and that is not entirely obvious. Noticing that cosine and sine are both bounded between -1 and +1 is very useful. And then the next question you might ask is, why don't we care about 1 over x squared being less than or equal to this guy? The point is that 1 over x squared is the smaller function compared to 2 plus cosine x over x squared. And so since the smaller function converges, that doesn't tell us anything about the larger function. Once again, if we draw our picture, suppose we have our smaller function and our larger function. If the smaller one has a finite area, then I don't know anything about what happens with the larger integral, right? I wouldn't know anything about what happens with this guy up here. And so the fact that the smaller integral converges is not helpful for us at all. We have to pay attention to what the larger function does. And so since 3 over x squared is larger than 2 plus cosine x over x squared, we can use that information to determine that our original integral indeed does converge. Whew, all right. Summarizing, final slide. Suppose we are trying to evaluate the integral from a to infinity of g of x dx. So this is the unknown. This is the one that we don't know. We want to figure out if that thing converges or diverges. And suppose we already know information about f of x. So we know whether that thing converges or whether that thing diverges. Then we can use this table to make conclusions about our integral. If f of x diverges, for instance, and g of x is the larger function, then that indicates that the integral of g of x also diverges. However, if f of x diverges and it is the larger function, so picture again, here's f of x, here's g of x. If f of x has an infinite amount of area underneath it, then that doesn't tell me anything about g of x, so I make no conclusion. And then similarly for f of x, if we know that it converges and we know that f of x is the larger one, then that implies that the integral from a to infinity of g of x converges as well. And that is section 8.9. If you guys have any questions, feel free to let me know. I'm always happy to answer them. Remember that you guys have some online homework due tonight and also due on Friday. Okie doke. Yeah, let me know how you thought this online lecture went. We'll be able to spend a little bit more time in class working on examples, so hopefully that is fruitful. Alrighty, toodaloo. See you all Friday.